So we are talking about nucleophilic substitution reactions. From the word, you have got nucleophilic, and then we are talking about substitution. So this is a kind of reaction where a nucleophile is going to be substituting another molecule where it is. Now, let's say you have got a compound like this. This is X, and then it is attached to CH3. Let's say the nucleophile here is hydroxide. This hydroxide has got two electrons. That's what makes it a nucleophile. Nucleophile is a compound that loves the nucleus. Nucleo, nucleus, phile, to love. So what is found in the nucleus are protons. So a compound that loves the nucleus, we are saying it loves protons. And since protons are positive, this compound should be negative. So all nucleophiles are either negative or they have got lone pairs because the electrons that are attracted to the nucleus. So what happens that this lone pair of electron will go and attack the nucleus of this carbon that is containing this X. So X is known as the leaving group, and as you can see, I've written a full arrow. I didn't write an arrow like this. It's a full arrow, meaning that two electrons are both moving. And when this happens, what will happen is that this bond is going to break. When a bond between carbon and X is an halogen. Halogens are more electronegative than carbon. So when this bond breaks, it is the X which is more electronegative, or the halogen, that will end up taking the two electrons. And so what we are going to see as a product will be now HO being attached to CH3. And then you have got X alone. Okay, it has carried those two electrons, so it will become negatively charged. So this is what we call a nucleophilic substitution reaction. Now you need to know that not all nucleophiles can displace all leaving groups. It's only when the nucleophile is stronger than the leaving group that is when the nucleophile will be able to displace the leaving group. So that's why you need to know the strength of nucleophiles comparing the relative strength of nucleophiles. And how you know the strength of a nucleophile is looking at the strength of the base. All nucleophiles are potential bases and all bases are potential nucleophiles. Therefore, stronger bases are stronger nucleophiles. Okay, so I've already mentioned of how nucleophiles are. Nucleophiles either have got a negative charge or they have got lone pairs of electrons. For example, hydroxide, it has got three lone pairs of electrons. It has a negative charge. Chloride ion, you also have this one. Water is also a nucleophile. Even a double bond acts as a nucleophile because there are some electrons there that can get to attack another compound. An electrophile is a compound that loves electrons, meaning that it should be positively charged because the electrons are negative. For example, H plus, CH3, CH2 plus. Compounds that are positively charged, we call them electrophiles. Okay? So what happens is this, look at this. If you have got a carbon that is bonded to another carbon and then it has got hydrogens throughout like that. As we go on with reaction mechanisms, you understand that we can have an alkane like this one forming an alkene. What we can do is that we can just use a molecule to come and grab one of these hydrogens. This bond will break and form a double bond here. When that happens, even this bond here will break. Okay, what I'm saying is that you are going to have a double bond between the carbon atoms and then you are just going to have two atoms attached to them. But then if you have got a double bond like this one, if I come and attach, let's say, an hydrogen on this carbon, a carbon can only have four bonds. So if I attach an hydrogen on this carbon, it's going to have one, two, three, four, 5 the other bond that I'm forming, and that's not possible. So me attaching an hydrogen here will mean that this double bond will break. And so what we are going to have is a carbon bonded to a carbon, and then you are going to have a bond, that hydrogen that I'm attaching, plus remember there are already these two bonds, like that. The double bond has broken. Same way, this carbon has got a bond, this one, and also this one, like that. But what has happened is that this carbon that attached the hydrogen has got 4 bonds, it's still stable. But the carbon here only has got 3 bonds, 1, 2, 3. So because the carbon has got 3 bonds, less than enough is going to be positively charged. When a molecule has got a lot of bonds, it becomes more than enough, it becomes negative because bonds have got electrons. Less than enough, it becomes positive. Actually, that's known as formal charge. Formal charge is given by group number. Carbon is in group 4 minus the electrons in bonds, the shared electrons. So this one has got 3 bonds, 1 bond, 2 bonds, 3 bonds. So 4 minus 3, that gives us a positive 1. That's why you see this guy is positively charged. If it had also a lone pair of electrons, let's say like this, you count this one as individual electrons, so that would be 3 bonds plus 2 electrons, that would be 5, so it would be 4 minus 5, it would have given us a charge of negative 1. Is there any question? Is this clear? Are we moving together? Okay. So when we are talking about these reactions, we basically talk about alkyl halides. What's an alkyl halide? An alkyl halide is a compound that has got an halogen and an alkyl. An alkyl is basically an alkane, all right? An alkane, for example, you just have something like this. This is an alkane, but at the end you put an halogen. Let's say, for example, I put an halogen like fluorine. This is known an alkyl halide. So this fluorine is attached at this point is a carbon. There is no bond. There is no atom here besides fluorine. So this one is the carbon. So this fluorine is attached to 1, 2, 3, 4, 5. It is attached to a 5 carbon alkyl group. So we call this as an alkyl halide. So alkyl halides can react with nucleophiles to undergo a nucleophilic substitution reaction or a nucleophilic elimination reaction. In a substitution reaction, what happens is that we'll simply get one element, replace it with our nucleophile. But in an elimination reaction, what happens there is that from the alkyl halide, this guy, that carbon that is attached to the X or to the leaving group, we are going to remove one hydrogen from it. It's actually the nucleophile that will get an hydrogen from there. And at the same time, X will also leave. But in a nucleophilic elimination reaction, we form a double bond. We'll talk about the details of the mechanism later. But these are the two main reactions that you need to understand. So when it comes to nucleophilic reactions, we have got SN1 and SN2. Okay? SN like this. So SN1 and SN2. S is substitution, N is nucleophilic, 1 is first order, 2 is second order. For an SN1, let's start with SN2. SN2 reaction, what happens that when you have got your halogen, let's say not halogen, but alkyl halide. Let's say our alkyl halide is here. And then let's say the halogen there is X. X can be anything, right? And then this one is reacting with a nucleophile. it has got a lone pair of electrons. Now what happens is that for a nucleophilic substitution reaction, the nucleophile is going to attack the carbon that contains the leaving group, and it is this carbon here. So this one is going to come and attack this one. For SN2, it doesn't attack direct and then the bond breaks. Instead, we are going to form an intermediate. So this same carbon you can see here is going to have a bond with X. This bond is going to be breaking, while the bond with the nucleophile is going to be forming. So this is the intermediate we form. This intermediate is highly unstable. Highly unstable. Those positive charges are just meaning unstable. And then what will happen now is that the bond with the nucleophile will now fully form, while the X is going to break. So now you are going to have like this. Nucleophile has now attached, and then the X has left. Okay, like that. Because this bond was breaking. In an SN, this is SN2. It involves two steps. In SN1, we would not have had this intermediate. You can would have just gone direct to the product. Yes, please. Is there a question? Okay. So let's say, for example, we have got this question. We want to write a mechanism. Okay. I can also write this like this. We have got a bromine. It's attached to only one carbon. I can write it like this. There is a carbon here. It's the same. And then I have got hydroxide, which is the nucleophile. I'll just write a lone pair because it's the one that I'm going to be using to attack. So this lone pair is going to go and attack this carbon. This bond is going to be breaking. And before it fully breaks, we're going to form an intermediate. This carbon is going to have a bond breaking with bromide and a bond that is forming with a hydroxide. It's actually the oxygen that forms a bond with carbon. And then what is going to happen is now the bromine will fully break, the hydroxide would have attached. So we are now going to form this. There is a carbon here. This is methanol, and then plus Br. The Br would have gotten the two electrons from the bond that was broken, so it is going to be negatively charged. Does this make sense? Is it okay? Okay. So when you look at an SN2 reaction, it's important to understand that you actually have a nucleophile, and then plus you have got alkyl halide. How we represent alkyl halide is just X with R. R is the alkyl, X is the halogen. And then you are going to have first your intermediate. The R is going to have a bond with the nucleophile, and then a bond with the X, which is breaking. And then at the end, the bond with X will fully break, and the bond with the nucleophile will still fully form. This X would have gotten the electrons. So always need to make sure that we are showing arrows and they are shown correctly. This is what makes chemistry a bit tricky. So we can find the rate of this reaction. And the rate of the reaction is given by the rate constant K multiplied by, on the reactant you have got the nucleophile raised to the power 1 and then you also have the alkyl halide. So for SN2 reaction, if you double the concentration of the nucleophile, but you keep the concentration of the alkyl halide, the rate of the reaction is also going to double. If you double the concentration of the nucleophile, you also double the concentration of the alkyl halide, the rate of the reaction is going to increase by a factor of 4. You're expecting such questions in your questions that will be coming, so make sure that you get that. How about if we triple the concentration of the nucleophile but we double the concentration of the alkyl halide? The rate of the reaction is going to increase by a factor of 6. Are we moving together? So again, you can see, okay, you have got another mechanism here. Hydroxide is reacting. This is a tate butyl bromide. The hydroxide is, please, for any mechanism, you need to show arrows. This is not a mechanism here. So the hydroxide is going to go and attack this carbon. This bond is going to be breaking. Before it fully breaks, there's going to be a point where you have got a transition state. Now, oxygen is more electronegative than carbon. Halogens are more electronegative than carbon. That's why you can see the oxygen is carrying a partial negative charge. Bromide is also carrying a partial negative charge. The carbon is going to have partial positive charges. And the next thing that will happen is that the bond with the bromide will fully break. The bromine has actually now carried those 2 electrons, and so it's now negatively charged. And then the bond has now formed with the hydroxide. One important thing that you need to know about SN2 reactions is that when the reaction happens, there's going to be reverse of configuration. That is why when we started learning chemistry, we talked about electronic configuration. If you don't know how to write the SR configuration, the easy configuration, please go through on the drive. Okay. Look at this molecule here. How do you determine the configuration? Look at the carbon. You look at the atoms which are directly attached to the carbon, and then you look at their molar mass. So to this carbon, you have got a bromine, you have got a hydrogen, you have got a carbon and a carbon. Bromine has got a smaller mass, so I'll give it a number 1. But I've got 2 carbons. So because there are 2 carbons, look at the atoms attached directly to those carbons. For this one that is on top, it's actually attached to another carbon which is here. For the one that is down, it is attached to hydrogen. And we know that carbon has got a higher molar mass. So therefore, this one is the one that will carry the second priority, and then this will be the third priority. Now, the least is going to be a hydrogen, and we don't even show it's supposed to be number 4. And then you now count the numbers from 1 to 2 to 3. Look at how the arrow will move. So the arrow is going in this direction. Okay. So this is known as this configuration. If the arrow is going like this, that's known as the arrow configuration. But for you to determine that, you need to make sure that the fourth group is at the back. How you know that it's at the back is that it should be on a dash. If something is on a wedge like this is meaning that it is in front. So this is the S configuration. So when your reaction is happening, you need to make sure that the product that you write should have a different configuration. Okay, should have a different configuration, because if I just replace this hydroxide, I remove the bromide here, and then I put hydroxide there, it will still be the S configuration, but I want the R configuration. And it doesn't mean that for the other configuration I should get the hydroxide and then put it, if this one was at in front, hydroxide should be at the back. No. The best thing that you can do is just swap any two groups. Okay, just swap even one group. That can be okay. Or swap any two groups. So just get this hydroxide, come and attach it here, but you swap some groups there. So since we are going to have hydroxide at this point, you swap these two groups. If you swap these two groups, what you are going to see, you are going to have a carbon, CH2, CH3, and then hydrogen is still at the back. And then if I swap those two groups, we are going to have like this. Hydroxide will be here, and then CH3 is going to be here. So if you count these guys, this will be number 1 because oxygen has got higher molar mass. This will be number 2. This will be number 3. So you can see if you count from 1 to 2 to 3 like this. This is the error configuration. That's what you can do. You just swap any two groups. Okay. Especially those two groups which have got priority. In case I swapped two groups and then it didn't give me the error configuration, I would have swapped other two groups until it gives me that configuration, the opposite. So make sure that there is reversal of configuration after an SN2 reaction. I hope we've gotten that. That is very important. So there are factors that will make a reaction to favor SN2 instead of SN1 reaction. So the first thing is the structure of the alkyl halide. The reactivity, methyl halides will show a faster reaction than primary, than secondary, than tertiary. So a methyl is something like this. Let's say I've got a bromine, it's just attached to one carbon like that. One carbon is a methyl, so this is a methyl bromide. This is going to be faster than when we had a bromide attached, let's say like this, attached to this carbon. This carbon here is a primary carbon. Why? Because it is attached to another carbon. It's a primary carbon. And this reaction is actually going to also be faster than a secondary. Secondary is something like this. You have got a bromide attached to this carbon, but this carbon is attached to two other carbons. You also have a tertiary alkyl halide where this carbon is attached to three other carbons. This is tertiary. Now you need to explain why the reaction is going to be faster for SN2. It is faster because of the halogen. Let's say the halogen, not the halogen, but the nucleophile. When the nucleophile is coming to attack here, it is going to easily attack than coming to attack here. Why? Because this other carbon at this point has got some electrons that will be hindering the nucleophile from attacking this carbon. And it is even worse here because you have got a lot of carbons. And even much worse here because you have got a lot of other carbons that are obstructing the nucleophile from attacking. So we call that as a steric hindrance. So the reason as to why this reactivity is like this is because of steric hindrance. Tertiary alkyl halides are more sterically hindered than the methyl halides. And that's why the reaction becomes slower for tertiary guys. Another thing that favors SN2 reactions is a strong nucleophile. And we did talk about the strength of nucleophiles comparing which nucleophile is stronger than which one. It's just looking at bases. Okay, you can just check that class on comparing the strength of nucleophiles. It's very important for you to go through it, because if they give you a reaction, let's say you have got ammonia and then you have got water, these guys are competing as nucleophile. Which one is going to be faster? You need to know. Water is going to be a stronger nucleophile because these guys are in the same group. Like oxygen is here, nitrogen is here, fluorine is here. Fluorine is the most electronegative guy. So the closer you are to fluorine, the more electronegative you are. Oxygen is more electronegative than nitrogen. The meaning of that is that when water forms an ion, when you lose that hydrogen, when you lose one hydrogen to form hydroxide, the anion you are going to form is going to be much stable than when ammonia loses an hydrogen. So that explains the stability as to why water ends up being a greater, a more, a, a stronger nucleophile. It's because of the stability of the anion that will be formed. But when you go down the periodic table, it becomes different. When these guys are attached to hydrogens, they become acids. And the strength of an acid depends on how easily it can let go of an hydrogen. And the more you go down, the bigger the atom becomes. So bigger atoms are going to actually act as, okay. I hope you I hope I haven't lost you too much. Are we did you get about the strength of water and ammonia? Which one is stronger? Okay. So I'm talking about now the strength going down a periodic table instead of in a group. You have got hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. When you are going down the periodic table, atoms are becoming bigger. The bigger the atom, the easier it can lose an hydrogen, just like you, right? The bigger you become, the easier it becomes to lose you, because you want to be independent, you want to do what you want. Atoms that can easily lose an hydrogen form stronger acids. So this one is the strongest acid in comparison to the others in group 7. Now the guy that forms the strongest acid will actually form the weakest base. When you lose an hydrogen, the I minus that you form is a base. Same with the Br minus is a base. So in this case, Br minus is a stronger base than I minus iodide. And because nucleophilicity parallels basicity, it means that this is a stronger nucleophile because it's a stronger base. So if you have got a competition where Br and I minus is supposed to react, Br will end up winning because it's a stronger base. So that's about nucleophile. And about leaving group, the stability of the anion of the leaving group and the weak bond strength of the leaving group will increase the rate of the reaction. For example, let's say if you are comparing chlorine and Br as leaving groups. When you look at these guys, you need to know which one is more stable. Okay, which one is more stable? You can look at their electronegativity. Chlorine is closer to fluorine than bromide. So in that, it tells you, let's hope I've written this correctly. If not, bromide is supposed to be on top. So an atom that is more electronegative can accommodate this negative charge so easily, this negative charge that will be formed, because leaving groups will always, most of the times, will have that negative. So if something can stabilize that negative, it means that's a better leaving group. If it has got a higher electronegativity, it's a better leaving group because it can accommodate that negative charge. A solvent is also very important when it comes to SN2 reactions. SN2 reactions are favored by what we call polar aprotic solvents. You need to know why. What do we mean by polar aprotic? This is a solvent that is polar, meaning that it has got positive charges and negative charges, but it is aprotic. Aprotic means that it doesn't have protons. It should not form hydrogen bonds. Okay, so those guys that don't form hydrogen bonds are going to end up favoring SN2 reactions. You need to know the reason as to why it is polar aprotic that is favored. Okay, just hear what I was telling you about the leaving groups. You can see if you have got iodine and when you have got fluorine. So here the explanation is the weaker the basicity of the leaving group, the better it is a leaving group. So you don't only talk about electronegativity, you're also talking about basicity. I said we have got fluorine on top, you have got chlorine, you have got bromide, and then you have got iodide. And we said that when you're talking about bases, the strongest base is this one because it's coming from the weakest acid. And the thing is, the weaker the base of a leaving group, the better its ability to leave. So that is why, since iodine in this case is the weakest base, it will end up being the best leaving group, okay, because it's the weakest base. So when you're comparing chlorine and bromide, instead of using electronegativity, you are going to use basicity. Br is a better leaving group than chlorine. Why? Because Br is a weaker base in comparison to chlorine. Hope that is clear. And when you're talking about the solvent, you have got a polar protic, polar aprotic. Polar protic includes, let's say, water. Water is polar, but it can also form hydrogen bonds. Alcohol also can form hydrogen bonds. Dimethyl sulfate can form hydrogen bonds. Okay. But for something that is aprotic, it cannot form hydrogen bonds. An example that we can give is dimethyl fluoride, DMF. You can see the structure: acetyl, nitrile, dimethyl sulfate. So the reason as to why polar protic solvents are not good is because if you have got a solvent that can form hydrogen bonds, what it will do is that solvent will end up surrounding the nucleophile. When you surround the nucleophile does not have an ability to attack the electrophile. Because it cannot attack the electrophile, it becomes weak. And so that's why polar protic solvents are bad. Okay? SN1 reactions, as I said earlier, they only involve one step. You are just going to have the nucleophile attacking the alkyl halide. This bond then breaks, and then you form the nucleophile attached to the other group. So in this reaction, the rate of an SN1 reaction does not depend on the nucleophile. It only depends on the alkyl halide. Okay? Why? The concentration of the nucleophile really doesn't affect the reaction. That's why the rate of the reaction for SN1 is just K multiplied by the concentration of the alkyl halide. The meaning of this is that you can double or triple or quadruple the concentration of the nucleophile, but it will not affect the rate of the reaction. But if you double the concentration of the alkyl halide, you also double the rate. So that's what you need to know about SN1 reactions. For the factors that promote SN1 reactions, it's just the direct opposite. Tertiary alkyl halides are better than secondary, than primary, than methyl. SN1 reactions speeds up with a good leaving group, just like the other one also. And a good leaving group is weak base. Okay, just a moment. Okay, so a good leaving group is a weak base. Okay, sorry, I don't know what's happening really to this network. Okay, so I'm saying that for SN1 reactions on the structure of the alkyl halide, it will be opposite to the SN2, but on the leaving group it's the same. Okay, weak bases are better leaving groups. For nucleophile, the strength of the nucleophile does not affect the rate of SN1 reaction. So whether you have got a strong nucleophile or a weak nucleophile, we don't care. Actually, weak nucleophiles will even be better. And then for the solvent, polar protic solvents are better instead of polar protic. So you need to understand why. Okay, it's very, very important for you to understand why. Okay, let me just explain it from this same point, from this same board here. So in an SN1 reaction, what is going to happen is that look at the reaction. It is do I have any mechanism? Okay, for SN1 reaction, we form what we call a carbocation in the mechanism. You can even see here. So let's say, for example, you were told that this guy, this one, is reacting with a nucleophile, let's say hydroxide. They say write the SN1 mechanism. The first thing that happens in an SN1 mechanism is not the hydroxide going to attack. Instead, it will first be the BR itself leaving. When the BR leaves, this carbon here, because it has lost one bond, is going to become positively charged. This is a carbon, so that will be carbo. It's a cation, is positive, so carbocation. Now this carbocation has to be stable. That's why we are looking at now secondary, tertiary, quaternary. For if the carbocation is like this is tertiary because it has got three things. The carbocation is like this is secondary. The carbocation is just like this is primary. And then if you just have one carbon as your carbocation, this is a methyl. The more the alkyl groups that attach to the carbocation, the more stable it is. So that's why this one is very much stable for SN1. But remember, for SN2, we didn't have the formation of a carbocation. That's why the most stable was this one. It would have been the fastest because our interest was we were first attacking this guy, and so we needed the compound to be free. So that is explanation. And then when you are looking at which other thing are we looking at for SN? When you are looking at the solvent, polar protic solvents being good. So polar protic solvents is because of the carbocation that we are forming. Remember, step 1 will be the formation of the carbocation. Let's say this is a carbocation. A protic solvent can form hydrogen bonds. In other words, it will be able to stabilize this molecule. When you have got protic solvents, they'll be able to surround this molecule and then it will be stabilized. Okay? Like those solvents which can form hydrogen bonds, they will surround this molecule, they will stabilize it. That's known as solvolysis. So because this molecule is going to be stabilized by the polar protic solvent, that's why polar protic solvents become better for SN1 reactions. Basically, that is it about these reactions. Okay, we have got some questions from the tutorial sheet. I want you to do this. You can screenshot that, or you can find the questions on the drive. What happens to the rate if the concentration of Rx is quadrupled and the concentration of the nucleophile is doubled? And what have we been told? Yes, please. Sure, please go on. Okay, the rate of the reaction will be 8 times faster. So it is quadruple, that is, so X is, Rx is 4, and then the nucleophile is doubled. Okay, the rate of the reaction will be 8 times faster. That's true. Assuming this is an SN2 reaction. Because if it was SN1 reaction, the rate would have just doubled. So in that case, you need to know by what mechanism this reaction will go, because we've not been told. So how did we know that this reaction is going by SN2? We looked at this. We looked at this. This is a primary alkyl halide. And you know that primary alkyl halide prefer going by SN2. That is why this will go by SN2, and then the rate depends on both the nucleophile and the alkyl halide. This one is saying arrange the following alkyl bromide in order of decreasing reactivity in an SN2. 1 bromo 2 methylbutane, 1 bromo 3 methylbutane, 2 bromo 2 methylbutane, and 1 bromopentane. Please answer this one and send the solution. I want to see what you are going to do. What product would be formed from SN2 reaction of the following? 2-bromobutane and hydroxide ion. Try that. R2-bromobutane and hydroxide ion. Try that. S3-chlorohexane and hydroxide. 3-iodopentane and hydroxide. I want you to try those also. Write the mechanism and also the name of the product. So this question was from the tutorial sheet. Also predict which reaction would proceed faster. So looking at the features that we've talked about, you identify which reaction is going to be faster. So for one, we have got reaction 1 and 2. We have got chlorine here and iodine. The rest are the same. Which one will be faster? Reaction 2, what has changed is the nucleophile. Here we've got a nitrogen. Here we have got a phosphorus. Which one is going to be faster? Reaction 3, what has changed is also the nucleophile. Which one is going to be faster? Try that and also share your solution. We see which one, what you are going to find. Indicate whether the following solvent is protic or aprotic. Can they form hydrogen bonds or not? We'll also try this one. Arrange the following alkyl bromide in order of decreasing reactivity in SN1 isopropyl bromide, propyl bromide, tet-butyl bromide, methyl bromide. You can also try out that. And then the very last one, arrange the following alkyl halide in order of decreasing reactivity in SN1. 2 bromopentane, 2 chloropentane, 1 chloropentane, 3 bromo 3 methylpentane. The only way you can become good in organic chemistry is you answering questions and being corrected. Otherwise, do not be too good, right? Thank you so much. So we'll end here.